So far, we've talked about the history and where the traditions come from and some of the things that are being carried forward and why we do some of the things we do. We've also looked at some individual cases of inventors and their stories and the action and how they've culminated and worked together. Today, we're going to start talking a little about creativity and the visual nature of design. Because I think people tend to underestimate or misunderstand design as a process. But first, it's kind of interesting. Have you ever paid attention to the forecasts of futurists? It kind of surprises me that these people are paid because they come up with these all sorts of things. Their forecasts are almost never true. And when I look at them, I just laugh and chuckle as a technical person, as an engineer. I think this is just absurd. I kept track over the years, just for the fun of it, of 50 forecasts I heard over the course of 10 years. And you know, none of them came true. None of them were even close. But I said, remarkably, they get published and reported and people are interested in them. Some companies, I worked at a company, I won't name them, a large Fortune 500 company at one point that even hired futurists to come and tell us what the future environment was going to be like. And as we sat there and listened, the technical people just kind of scoffed and thought, what a joke, but they were paid good money. Some of the ones that I kept track of that I liked the best was, one forecast was there would be at most a worldwide demand for 10 computers. This is back in the early days of computers made by futurists at IBM Corporation. 10. I've got more than that in my house. Another one. There will never be a need for more than 50 kilobytes of memory in a computer. Bill Gates is credited with saying that, and he did say it, but it actually was first endorsed by one of the futurists in electronic computing out in Stanford. What a joke! My computer downstairs has 4 gigabits of memory, and it's not enough. More than 50,000. What a joke. Another one. ICs will never have more than 1 million transistors. It's physically impossible. This was put out by a group of futurists at Stanford looking at the future of electronics. Today you buy a memory chip, and for goodness sakes, a memory chip often has a few trillion, thousands of times more than these forecasts would have. Or another one. Carnegie Mellon, in their future study, put out the world of the future, and one of their was by 2000. Household robots will be the norm. Well, I got news for you. It's well past 2000, and I don't know about you, but I don't have a robot running around taking care of my house. Or how about this one? That was a forecast that was made by one of the early studies out at DataQuest, who forecast the internet will never be of much commercial use or value. Well, okay. You know, what happens so often with technology is it runs right over the top of what people who are not watching it see, and it takes us in a direction that cultural and society wants. If you just talk to the people engaged in this technology, they know what's going to happen in the next 3 to 5 years. And frankly, beyond 5 years, nobody knows. The futurists are wildly wrong because the problem is that there is an intense interaction between economics, social pressure, political pressure, technology. And as a technologist, some things people forecast will achieve, I can tell you, not going to happen in 5 or 10 years. But other things, I just don't know, because there's the question, will the political process provide money? Will the people really be willing to spend whatever it takes? Are there going to be social forces that require us to do this? I have to say, when I first heard about Facebook, I thought, what a joke. Who'd want to do that? Piece of crap. Well, all my nieces and nephews are on Facebook, so I'm on Facebook. These things have a way of the complex interaction running over forecasts. But the only one who's got as bad a record as futurists I guess, is a weatherman, and that's one of the few things you could be wrong every day and still make a lot of money at. So maybe I should in the wrong field. I'm afraid I have to be right in my field, and I think I'd rather have that. Well, we're talking about creativity. Now, technical activities are extremely creative. There was a study when I was running an engineering group in Portland, Maine. There was a study done by the University of Maine up in Orono, and it was interesting. They gave a series of tests on creativity to a variety of students on campus, expecting, of course, the people in the arts and music would be the most creative. Guess what? The people who scored the highest on their creativity were the people in engineering. Because problem solving is extremely creative. Yes, you can go and I can show you in class, okay, you do this and this and this to solve this particular problem. But real problems aren't like that. And as soon as I give my students, go design something, they're faced with trillions of decisions, literally, and no fixed way on how to calculate or solve things, and their whole creativity comes in. The real world's just very creative and interactive, and one of the things that people don't realize is how important it is in problem solving to use multiple different ways to express things and think of problems. There's the visual way. The most powerful way to solve a problem is visually. When I have a problem, the first thing I've learned to do is get a picture in my mind. If I can see the problem and see what's going on, I can almost always solve it. If I can't see the problem, if it's unclear or fuzzy, if I can't get a picture, chances are I'm not going to solve it, or at least not get a good solution to it. So there's the visual. Studies have shown that visual is the one way of thinking where the whole brain lights up. Activities all over, highly distributed, very, very, very strong. Linguistic. We need words to talk about things. It may sound silly, but lots of times problems are not able to be solved because we don't have the language to discuss it. Putting things in language helps clarify what's going on and helps clarify relationships and exclude and include what's appropriate. And my process of having words and describing and talking with someone else is very important to getting my thinking to coalesce. And also, of course, there is the linguistic back and forth where I gain from you. Then, of course, there's the analytical way of solving problems, the expression and analysis, write an equation, write multiple equations and try to solve them, set up the problem. And of course, there's the numeric, where you just plug and chug numbers, maybe use a simulator and try to get it. All four of these ways of expressing, very important in coming up with solutions, most powerful being the visual. Well, what they find is when studies have been done is people in technology tend to use the expressions differently from other groups. There is much more emphasis on the visualization. Now, we're not talking about the student because the student's learning and gathering things. We're talking about people out doing the work. They tend to be much more visually oriented. The general population doesn't realize how visual the work is, but extremely visual. And then what happens is after visualization, people who are good at technology tend to translate the visualization into some sort of models. They define language that describes the models or the interactions and solve the problem. Here is a study that was done of how people's solution to problems change over time. And what happened was they took a group of engineering students, just starting. Then they took a group that had graduated and worked 1 or 2 years as an engineer. And then they took those who had been distinguished in some fashion, chief engineer, head engineer, or something. They took these 3 groups and they gave them all the same type of problems to solve. Now, their goal was then to see how much of their time they spent on different activities. The 3 activities were visualizing the problem, modeling the problem, and calculating the problem. How long did they do these? 3 did they spend on it? Of course, not shown here is the fact that the chief engineers always solved the problems, and the students often couldn't get a solution. We're not as interested in did they get a solution, although that's important, but how much of their time are they spending? What are they doing? Well, you notice here, look at the visualization line. The engineering students are spending 12–15% of their time seeing the problem. Chief engineers are spending over half their time seeing the problem. And as you move down, you see, well, the chief engineer then spends only a short period of time ready to model, whereas the students are spending over half their time trying to develop a model. By a model, we mean equations and other things that you could calculate with. And in the final end, the chief engineer, 10% of the time calculating it. A student is 30% or so. Quite a difference. You can see the better someone is at technology, the more experienced, the more and more the visual. This usually surprises most people. But I have to say, when I have a problem, if I get a problem, or when I'm teaching, you take one of my classes, and I will show you a problem, and the first thing I'll start talking about is, well, notice this pattern. See this grouping. Can you see how this current moves here? Can you see how it moves there? And as soon as I can see it, I can usually just write down the answer, because I can see it. This is extremely important skill, and one that people continually develop as they get better and better at technology, the visual. It's also true, you go to the general population, and you see it's even worse in the general population. Now, I've added to this chart how often the people solve the problems. And so we have the general public, only 20% of the time they solve the problem. These weren't hard problems, so it's surprising they were that quick. Chief engineers, well, they always solved it. It says 95, they always solved it. Even the 1 or 2 year engineers, there are a few of them that muffed it probably because they weren't paying attention, but they basically solved it. But look again at the change. What does the general public do for visualization? 5% of their time. They spend almost all their time trying to do a model. Whereas the chief engineer, someone who's really good, what they do is they look at it, think about it, say, oh, they write down a model, and they're done. Again, the visual is very strong. It is the strongest. The analytic, when you do analysis and watch the brain, it's only a small portion of the brain that's active. Same when you're writing down a model, it's only a small portion. When you're thinking and doing visual, the whole brain lights up. It's the most powerful. The problem is that it is a skill, it takes practice, it's something that is learned. Some people are just born seeing things, and that's great, but it's also something that can be learned, developed, and grown, and most of us don't do that. And so you see the general public down here hardly spending any time envisioning things and just trying to blindly quick write something down, because, well, it's also true, despite what people tend to think, real technical problems never have one solution. They always have multiple solutions. There may be a best way to do something, but even the best way has multiple different implementations to do it, and so there's lots of different ways. Now, a typical little sort of technical problem might be if I give you a problem, I say, design a fax machine. Well, there's lots of questions. Supposed to be really expensive? Is it really nice finish? Is it going to look pretty in the room? Do I care if it works when it's wet outside? What about if I'm in the middle of the Sahara Desert? Does it have to work? Does it have to work if I'm out in the Antarctic? Should it be real small? Should it be real light? Do you care? Does it have to run off a battery for months? Is it portable? Am I just going to take it, set it up? How fast does it have to be? There's all sorts of different parameters, and all of them have different implications on how I might do the design. And even after I answer all these questions, there's still 1,000 more questions. There is no real simple solution. I don't care what the problem is. And so much of the solution then will depend on how I see it and what choices I see. Here's another question. You say, well, how about something simpler? Your fax is too complicated. You purposely tricked us. Okay, I'm designing a chair. How high shall I make it? Well, what country am I going to sell the chair in? The average Chinese is probably about that tall. Average American, I'm probably about average for that. If I'm selling it to Zulus, probably taller. If I'm, and so forth. So what country? But even within the country, what age? I remember being in Spain. I'm in the middle of Spain in Soria, walking around, and I noticed something really interesting, at least to me it was. All the people, late 60s and so forth, are about that tall. All their kids are about that tall. Why? Well, in the middle of Spain, prior to World War II, not much protein. Everybody's short. After World War II, things changed, conditions changed, more protein. Everybody's tall. Who am I selling the chair for? People this tall or that tall? How old are they? And another question, what do you mean by optimum? You know, if I'm an old person, I want a chair that's high enough that I just slide out of it, because it's hard to leverage yourself standing up as you get older. And so I want a higher seat that I slide out of. If I'm a younger person, I generally want a chair that kind of slants back and is low, so the chair takes all my weight and I can sprawl. What do I mean by optimum? So even a simple question like design an optimum chair height involve lots of ideas, discussion, and how I see it. How do I visualize it? So what happens are technical activities and problem solving tends to proceed from a philosophy. And a philosophy is my beliefs about the object, my goals, my directions. What do I believe? It's most technical people have a hard time thinking of this as and saying, oh, I don't have a philosophy, but they do. You go to companies and you can tell what their philosophy. As a consultant, when I go to a company, one of the first things I try to understand is, what is this company's philosophy? What does this group within the company believe about their products, their customers, what their goal is, what they want to do, where they're headed? These are very important things because the philosophy, the beliefs shape what we do. It's extremely important. Now, here's a classical problem that I like to give because I think it illustrates the sort of thing that happens. Because there's lots of problems that can only be solved in certain ways, especially problems that are really only solved visually, or at least best visually. And so here's a classic visual problem. It's called the classic monk problem. Let's say, here we have a mountain and a monk. And let's say that this monk decides to visit a temple on the top of the mountain. He lives on the bottom. Now, in the morning, he sets out walking to the top of the mountain, and it's on a winding path. It kind of goes high and fast and low and swoops around the mountain, only big enough for one person to walk. And he sets out at 8 o'clock in the morning, walks all day. He might sit down for a while, he might stand up, he might take a nap, but it takes him all day. 4 p.m. he gets to the top of the mountain. Now he prays all night. Next morning he gets up at 8 o'clock. So he's going to start at the same time, but now he's starting at the top rather than the bottom. And he walks all day, gets to the bottom of the mountain at 4 o'clock at night. So here's the question. Is there any one point on that trail where he's at exactly the same point at exactly the same time on both days? Well, this is a visual problem. There is a way to solve it with transformal topology. Most people have never even heard of that, much less done it. So there's no realistic way to solve it with an equation. I've had students sit down and start writing equations and they're lost. I've had students start making a model and they're lost. Because you can't really solve this problem this way. There is a simple solution. By the way, it's an important problem because it has to do with placement, routing, and switching networks, so it has applications. The solution does, understanding the solution at least, has applications in things like telephone switching and that. So it's an important problem, historically. But the answer is yes, there is one point. Is there more than one point? No, there's only one point. One point and only one point. Important thing to know. Why? Well, look, think of it this way. Start one monk on the trail at the bottom at 8 o'clock. Start the other one at the top at 8 o'clock. So all you're doing is you're superimposing the 2 days of walking. Have the one at the top walk down, the one at the bottom walk up. Question, will those two monks meet on the trail? Of course they will. Will they always meet? Of course they will. Will they meet more than once? No, because one's up one's going up, one's going down, they'll meet once. Where will they meet? I have no idea. But they will, it will happen. And that was the whole question. Now you see how easy this is to see in my mind. In my mind, I can see one walking down and one walking up, and I immediately see they will meet somewhere. I just don't know where, but it will happen. And it will only happen once, because one keeps going up, one keeps going down. This is a visual problem. And it doesn't matter how long you spend on your models or equations, unless you're good at transformal topology. It doesn't matter how long you spend on it. You're not going to solve this problem. The only way is visual. Many, many problems really only have, in a practical sense, visual solutions, and you must see them and see what's happening. And many problems in technology are really only solvable visually with today's science and understanding. This is part of why, when I talk, I say engineering technology is ahead of science. Because engineering technology, we often solve many problems where there's really no science or way to calculate, at least not at the current time, the answer, but we can see what to do. And so we do it. It's a visual sort of thing. Well, design is probably the most creative of all. But a lot of people think, by the way, when you say design, you're talking about a new product. I'm going to design a new TV. Well, that's one type of design. But there's also, I'll design a new industrial process. I'll design adapt, design a change to this machine to work better. I'll design and so forth. So all sorts of things get designed all the time to make our lives better and work smoother. Now, most designs generally begin by examining what has been done before. Why? You're trying to build up this visual imagery. You want to build up the understanding of what's happened and see it, and this lays the groundwork for further visual development. And so you find technical people tend to continuously study history and current competition. When I was actively designing chips, we routinely went to the conferences where people talked about it, read all the journals, and if there was a particular type of electronics we were interested in, we would buy competitors' chips, take them apart, look at them, see how they worked. And that is called reverse engineering. Reverse engineering is, by the way, a recognized field. And what it means is you give me a product, I take it apart, I tell you all the details of how it was made and how it works. It's a major business, by the way. Last time I looked, I came up with 43 companies whose sole business was reverse engineering. There's probably more. But the point is, there's a lot of companies that just do this. And what do? Well, you send the company a product and tell them, I want you to reverse engineer and tell me the details of how it's built. And because they do it all the time, they're quicker and faster than you are, and so they can quickly take it apart. Sometimes they already have records of other work they've done like it, and they send you a report. In the early days of RAM, for example, random access memory, when we were doing those, there was a company called MOSAID up in Canada where we used to send chips for, routinely send RAM chips. They take the chip apart, they do all the logic, they tell us how it was made, how the layers were and everything, send us a complete report, usually within a few weeks. As things got more complicated, they started making standard reports people would buy. I can remember sending them microprocessors, saying, well, you know, Intel had some, we were making microprocessors. We want to know the details of it. And send them an Intel chip, send them some money, they'd send me back the complete reverse engineered. Why? Because this is important to see how other things are done and other solutions. It starts with a whole visual process and gives me other ways to compare. Because solving things visual depends on your visual memory of other items and the similarities you can draw and how your mind can go from this visual path to that visual path and make changes in between. Very important. Well, this means, of course, that when you look at things, you tend to often draw imagery from the past. And so in understanding visualization, again, we're going to turn to some examples from the past. And that means most of our examples are going to be civil or mechanical devices because that's generally what we have a long history of and we can look in the distant past but it's certainly true that one of the more abstract fields, electrical engineering, probably is more visual than most. In fact, it certainly is. In electronics, it's largely visual because you can't see anything. You can't see the electrons and volts, and so you can't see many things. So it's very highly visual, but we're going to look mainly civil and mechanical because that's kind of what we have the record on. Well, seeing is knowing. If you can see something, you know something. As I've said, in my 20 plus years in industry and designing and solving problems, I always found if I could see it, I could solve it, I could fix it, I could improve it. So the first thing was always seeing. Well, the nature of engineering design. There was a report done for American Society of Electrical Engineers on engineering design, and I quote from it. It is usually a shock to students, engineering students by the way, to discover what a small percentage of decisions made by a designer are made on the basis of the kind of calculation he or she has spent so much time learning in school. It is true. Educationally, people tend to think, well, we're spending all this time on calculations and that must be all we do. And I think that's probably why the population gets that. But in actual fact, we spend so much time because it takes a long time to learn how to do it, in addition to which, in the process of showing students how to do it, we build up their visual memory by showing them problems, and here's our solutions. So we've done two things at once. Once they're done, and they have the visual memory, most of their decisions can be made without having to do the calculations, but people don't realize that. Here's another one, IEEE committee, looking at the process of design, said, despite numerous efforts to systematize design activities, it is still true that the practice of engineering design is more artistic and less scientific than anyone wants to admit. In point of fact, there's often no reason than because I saw it that way for the numerous decisions made in the design process. This was a result of a long study by the IEEE, the Electrical Engineering Professional Society, on how design is done and how people make their decisions. Because the goal was thinking, well, if we could find out a very regular, systematic way, we could train people in that way and we get quicker, better designs. And they found out you just can't. It's just made because you see it that way. When I think of the things I have designed, I would say 90 to 95% of the time, the reason it was designed the way I did it was because that's the way I saw it. Yes, in the final analysis, I might say, well, okay, I'm going to do this in this way with these elements. And I would calculate, and I would spend a fair amount of time calculating the details of those elements to see exactly how big or how strong or whatever, because I wanted to tune them to the best optimum. But first, I had to decide this is what it's going to look like and how they're arranged, and this is how they work. And I did that because that's the way I saw it. Now, of course, I didn't just see it that way because it came out of a vacuum. I would see it that way because I had solved other problems that were similar. I'd seen other people's solutions that were similar. I'd been in discussions where they're talking about similar problems. And of course, sometimes I just made the intuitive leap that, oh yeah. But still, there's this vast underpinning of visual information that goes into, yes, I see that. And so, why look at the visual anyway? Well, the main reason to look at the design and think about it a little bit is there is a very small number of engineers and designs that influence society. It's less than 1%. Less than 1% of our population are driving these sorts of decisions. And yet, there is a vast impact on our lives and society and culture by the decisions this 1% makes. The people who decided to make video games created a vast industry, and whether they meant it to have the impact it has, they still change dramatically how people spend their time. Video games, for example, are credited with a rapid, at least partially credited, rapid drop with activities like hunting or fishing or all sorts of outdoor activities by the next generation. I believe it's true. At the same time, it's also credited with developing lots of quick response and motor skills. That's probably true too. But the design decisions impact transportation, communication, control. I mean, just think of how it's changed control in the home. If I think when I was a child, a furnace, maybe 50% efficiency. Now my furnace in this home runs 98% efficiency. I've cut my amount of fuel in half. And the temperature's control's better than it used to be. And of course, if you go beyond that to the heat pump and the electronic ability to switch between heat pumps and outside, in the last several years as I put in heat pumps, I've cut my energy use again by more than half. So compared to when I was a kid, my heating use of energy is down by, probably a factor of 6. Enormous impact. That has an impact in the lifestyle, other things I can buy, other things I can do, and so forth. So that's why we look at it, is these decisions and how you see things, and what you decide, whether it's the look, feel, touch, or operation, has vast impacts on culture and society. And it's also true, by the way, that even though it seems otherwise, often the ability to design things, the ability to make and design things, drives a reality rather than the other. Classic example is the moon program. Now the moon program was first proposed by the engineering scientific community that said, we know how, we can build, we can go to the moon. Here we say, we can do this. It was 3 years before the government decided, yeah, we should do that. So the ability to do it, envision it, and see a solution drove the reality. How about the Hoover Dam? Electrifying millions, 4 years before the Hoover Dam was commissioned, government decided to do it. The engineering community was saying, hey, we can do this. We know how to design. This is a possibility. How about the telephone's driving reality? Remember we just talked about Bell. Bell thinks he can see it, he understands it. Business community, government, we don't want it, we don't want it, don't waste your time. Does it, and reality changes. And so the reality is often changed by our ability to design and build things, rather than the other way around. Well, finally, although we often wish this was not true, and we would like to deny it, still the ability to design and build has inevitably driven much of the development of civilization. Some of the first developments in technology and design had to do with agriculture and recording and being able to store, plow, and so forth. But from there it goes into the military. Whoever has a weaponry wins and drives civilization. If it hadn't been for superior technology and design and weaponry, the Roman Empire wouldn't have risen. The Greeks wouldn't have risen. South Africa, the Zulus wouldn't have been run over by the South Africans, and so forth and so on. And so the technology has driven much of history and much of civilization. Later on, of course, we have industrial mechanization, and that drove a whole new reality and a whole change in lifestyle and value and net worth of people. Most recently, communications. The internet spreading everywhere has made it very hard, if not impossible, for many governments to continue their activities as they used to. We see big changes in China and changes in Russia and changes in different countries where they've had to adjust to a greater flow and ability to get information around. It continues to drive changes in the world more and more and more. And so whether we like to admit it or not, the ability to design and develop has indeed driven civilization in directions not always the ones we intended, but it has clearly driven things. Well, design. There's a world of difference between the way a technical person, an engineer, does design and a craftsman does design. Although they are related. Craftsmen, remember, technical and engineering tend to grow out of craftsmen. It's not the other way around, but they grow out of the craftsman. And so what's What's the difference? Well, a craftsman tends to hold their design in their head. They tend to see it and that's where it stays. And then as they look around and see the materials, they tend to modify and change their design to fit what they have. And they usually, a craftsman sells to the user. So the craftsman designs, builds, sells. And so as they sell to the user and interact with the user, they can make a change in their design for the next one they make. And of course, since they're the only ones involved in this, the craftsman's the only one that has to see it prior to it being finished. And so they tend to all be unique. This, of course, poses a lot of limitations to design, because each item that a craftsman makes is indeed unique. That's part of why we value things as crafts, and we tend to buy them, because they're unique, and we kind of like that. But this means you can only make a small amount of each item. I only make as many as I make. I can't have 100 of me, so they're a small item. And since it's generally not possible to really refine how I make it and my art and to get just the right amount, things are pretty much overbuilt. I use twice as much material or 3 times as much wood, and so my costs tend to be higher than necessary, and you might think that makes things better, but not necessarily, because often the extra cost, the extra materials in the wrong place. So they're not optimized, but this is the consequence of the craftsman approach. Now here's kind of a craftsman's approach to axes. Gentlemen, I just took a picture of a bunch of axes I saw from this gentleman up in northern Minnesota who was making them, and they're nice, but you look at them and they are all different. They're all overmade. None of them are optimized for use, but they're kind of fun because this is the way a craftsman does it. An engineer would not do that this way, nor would a technical person. Because the engineering starts with a mental picture, but then from there you make the sketch and the drawing, you do the calculation, you refine it. And remember, we saw this sort of approach starting early on, but coming really to a fine line with the Romans, where I pointed out, they clearly recognized the designer is different from the builder. The craftsman, the designer, is the same as a builder. The technical person, the designer is different from, and many times, in today's case, the designer never sees a builder. He never sees it made. He never sees it built. You design it, you draw it, you specify it, you send it somewhere else. And remember, that's where inspections became so important, to make sure that we got what we wanted. That's why we had all these long plans and specifications. This practice dates back long ways. It allows for you to have multiple units and optimize the units and learn. It also provides input from a group of people. The craftsman holding his design himself basically gets no input from anyone else. Oh, a little bit as you look and talk to customers, but basically it's their design. The technical person or the engineer, as drawing it and getting it ready and specifying it, has other people review and input and refine. And so each item gets more and more refined based on this multiple approach. Well, producing the drawing itself, my design I see, I'm going to draw and sketch it. Producing that itself is an iterative process. Generally, when I design something, I start with a rough sketch, kind of sketch out what I think it's going to be. And the sketch helps me further visualize more details. Generally, when people first see something, they talk about 10 to 20 main things. A good person at visualizing will see with clarity 10 or 20 things, but not hundreds. And so making a sketch helps me release some of those details and allows me to look further. And so as I look those further, I can add progressively more details and more refinement. Because I release the 10 or 20, I can add another 10 or 20 in my mind and see more details. And also the drawings now are available for other people to look, and they can get their vision and make refinements on mine from their visualization of what I've done. So the engineer's approach would be to make drawings. Now, of course, here's a standard mechanical sort of drawing that's made. But this drawing, if you're used to the drawings and you've made them, you can look at it and you can see the part You can rotate it and you can see what's going on, and you can make suggestions on this sort of design. Now, making these sorts of drawings and visualizations involves a fair amount of knowledge, but the knowledge that's brought is very broad. It reaches beyond science. The problem with science is that it often leads to incorrect or incomplete conclusions. Not because the science is terrible, but because the science is concerned with what currently is. It's not concerned with what is not. We take what is and we try to project. But the projections are only as good as our model and understanding of what we currently have. And quite often the models are simplified, they usually are, and the understandings only involve our current conceptions, not what we might conceive of in the future. And so we often have incorrect or inability to project ahead. Classical example was back when a flight was first being conceived of. There are major studies done all over the world at universities about flight, trying to calculate and understand, can we fly? And all the studies and all the conclusions were that in order to get a plane to fly, you needed to achieve nearly perfect stability was the word they used. They all talked about nearly perfect stability. The idea being that if you sent something flying, it had to be on its own stable. If it tilts a little, it'll right itself automatically. No control. Well, trouble with it turned out part of the trouble with nearly perfect stability is if the plane automatically keeps holding itself in one position, the pilot can't get it to change. And so the plane takes off, and if everything's not perfect the moment it takes off, the pilot can't turn it or correct it or bank it, and the planes just were useless. And of course they were building these early planes trying to get them nearly stable, which meant that as a launch, they were never quite right when they launched, and the pilots couldn't do anything. So it was a real problem. Now, along comes the Wright brothers, and there were others too, but most famous probably the Wright brothers. Wright brothers designed and built bicycles. They understood more practical problems, and one of the things that was in their favor was with bicycles, you depend on controlled instability. That is, when you sit on a bicycle, that's very unstable. Any change, any direction, you fall. But what happens is as you start to fall, you lean your body and go back up. It starts to fall, you lean up, and anyone who's ridden a bicycle or watched a bicycle realizes what's going on is controlled instability. That is, the rider controls this instability so it goes back and forth, and they achieve the desired result under their control. Well, the Wright brothers realized this, and they realized what you really need was controlled instability in the plane, and they built that in and made them very successful. By the way, if you've ever been out to Kitty Hawk, fun to go, interesting place. Here's some pictures from Kitty Hawk that I took when I was out there. Here's Orville and Wilbur Wright, their flight in 1903 flyer. Basically what they did was they built the plane so you could twist flaps on the end, which would cause it to first want to go this way and then that way and this way and that way. And then when the pilot got in, as it took off, the pilot would keep twisting and adjusting. So the plane would start to go the wrong way, he'd twist it, it'd go back and twist it like riding a bicycle. Very successful. It's interesting though. The Wright brothers' success eventually convinced others, including universities, they were right. Bad pun. Still, the scientists continued to try to calculate, well, what's the degree of instability you need? Okay, we were wrong. You've changed the paradigm. And that's often what happens, by the way, is the paradigm's wrong. The paradigm being all their assumptions and how they think things work and so forth. Well, they changed the paradigm and showed that, stability is wrong. You need instability you can control. Well, they changed the paradigm, but now they want to know how unstable. Can we quantify and calculate that? Physics department in London, Paris, Boston, they all tried to understand, calculate, and quantify, and none of them worked. Meanwhile, the Wright brothers and other engineers out flying planes, they made a bunch of charts and codified things and started to design planes. That's still, to a large extent, how it's done, is with charts and graphs, and we still try to calculate some of these things, and some we do, but many are charts and graphs, and put them in a wind tunnel and see what happens sort of experiments, because it is the exact situation and the exact assumptions go beyond what we're able to do with science alone. Well, as a result of this sort of experience, you find engineering knowledge has diverged to a large extent from science. Engineering knowledge tends to look at relations between quantities. It tends to look at, in electronics, current, voltage, temperature, etc., rather than absolute laws. It's more interested in this happens, this happens, this happens, this happens. Not that you ignore absolute laws, but you add to them with all sorts of rules and understanding. In addition, engineering knowledge generally incorporates a framework in which decisions are made. And the framework has clear assumptions. If it's between 80 and 110 degrees, then the temperature coefficient is at this point, and so forth. And so there's a framework: temperature, humidity, what are the materials, and so forth. And it also attempts to encompass uncertainties, because after all, we never really know anything perfectly. When I build something, generally, I can only specify something within 10 or 15%. If I say a 1-inch wire, it might be 1.1. It might be 0.9. My design has to make them all work. If I was taking a strictly scientific approach, I'd say 1 inch, calculate it 1 inch, it works. But it isn't an inch. Not only that, ignore the fact it might be 0.9 to 1.1 inch. What about the resistance of the wire? Well, copper wire is, I don't know, 0.06. Yeah, but it might be 0.058 or 0.063. Or it might be fatigued. Or it might be hot and have more resistance. And you see, all of these uncertainties have to also be incorporated. And so engineering and technical knowledge tends to go beyond to incorporate all these sorts of uncertainties as well as the framework. Given all these additional needs and information, what you find is that the technical knowledge, of course it's closely related to science, but it goes beyond it. It has all sorts of things that you couldn't predict from the pure science. Temperature coefficient, they tend to run in some sort of curve. The science doesn't really project that. It says, well, maybe they are, maybe they aren't. And I can try to somehow explain it and kind of understand what's happening, but the science won't do it for me. So what do? I go out and I measure it. I chart it, I plot it, and I say, well, between here and between these two temperatures, I have this coefficient. And that's what I do. And that knowledge has gone beyond the pure science. This requires, of course, that technical solutions and technical people are very familiar with the real world, and that they can deal with this complexity and all these assumptions of framework and interrelationships in a visual type fashion. They can see how they interact, and that there's also some intimate knowledge of what are the limitations. When does this not apply, and when does it apply? And once you do that, then you have finally come to a better understanding of what it really takes and what the knowledge really is. Well, this is just our start of our look at creativity, visualization, and the art of design. We'll continue on next time. In the meantime, have a good day. We'll see you later.